Today, Jordan Marsh from University of Edinburgh will give a talk about CARME CRYRING, so nuclear reaction measurements using stored ions. And so Jordan is a young postdoctoral researcher at the University of Edinburgh that is focused on experimental nuclear astrophysics, and more precisely, on the usage of storage ring for nuclear astrophysics applications. He also spent his PhD in developing the CARME setup at CRYRING, which obtained some first beam time recently. So hopefully some very nice results will come out of it. Additionally, Jordan is also working with the LUNA collaboration at Grand Sasso, always focusing on the detection of charged particles. And without spoiling anything else, please, Jordan, you can start your seminar.
Okay, thanks for the introduction. I'm happy here to talk about my work that's been ongoing at GSI in Darmstadt. So my talk will be on nuclear reaction measurements using stored ions. And in particular, as Jakob said, I'll be talking about the CARME charged particle array, which is installed on the CRYRING storage ring at GSI in Darmstadt. So first of all, I just want to give a brief word to one of the main focuses of nuclear astrophysics as a whole, and that's in the origin of the chemical elements. This plot is probably familiar to most of the people in the audience. It's the abundances of the various chemical elements in the solar system. We see very high abundances of hydrogen and helium, and then as we go to increasing mass number, the abundances slowly decrease with increasing mass. Now, overall, the outline of nuclear synthesis in the universe is quite well established now. We have Big Bang nuclear synthesis, which produced the light elements up to lithium. And for elements heavier than lithium, we produce those in various stellar sites through either quiescent or explosive scenarios. These can be things like supernova explosions, neutron star mergers. And although the outline of nuclear synthesis is quite well established now, there's still some details that we need to work out. And for that, we need to do some laboratory measurements to really pin down what's going on inside these various stellar sites. So first of all, I'm just going to briefly touch on the different nuclear reactions that occur in stars. One of the key parameters we want to know to help us with determining the abundances of different elements in stellar sites is the reaction rate in stars. The equation here that I've given gives the number density of our two interacting nuclei. We have our center of mass velocity of our two nuclei, and we also have the nuclear reaction cross-section. I've highlighted the velocity term and our cross-section here, as both of these have really strong energy dependencies, and the interplay between these two energy dependencies can tell us about the energy region of interest for various different stellar sites that we're interested in. So first of all, in a star, we have lots of nuclei that will be at many different velocities, lots of different energies, and there'll be a distribution of those. That's given by the Maxwell-Boltzmann distribution, which has this exponential to the minus e over kt dependence. And also we have our nuclear cross-section. Now, because nuclear reactions in stars often occur at sub-Coulomb barrier energies, they must proceed by quantum tunneling, which means we get this energy dependence, which is the exponential of the minus square root of the gamma factor over the energy. And this basically means that when we have high energies, it's much easier to tunnel through the Coulomb barrier compared to at lower energies where our tunneling probability is much lower. We can see this in the plot on the bottom right that I've taken from Nuclear Physics of Stars. For the oxygen-16 p gamma reaction, we can see the exponential dependence on energy for the cross-section. At low energy, it decreases by several orders of magnitude. Now, the interplay between the tunneling probability and also the distribution of nuclei in a star gives rise to this energy region where we have the highest probability of a nuclear reaction occurring. And this is called the gamma window, and this plot on the left here quite nicely shows this. And if we want to understand nuclear reactions occurring in different stellar scenarios, we need to understand our nuclear physics in this energy region, because this is where most of the reactions are going to be occurring. Now, if we have a smoothly varying cross-section, such as the one shown here, we can do a nice little trick. We can parameterize our cross-section and turn it into something called the astrophysical S factor. And this basically removes the very strong energy dependence. And we can see here that the S factor over the same energy range given in the top plot is basically flat across all energies. And this has the very nice advantage of we can perform a laboratory measurement at high energies where the cross-section is quite large. And then we can extrapolate that cross-section down to very low energies that we're interested in for stellar sites. And this can tell us about the nuclear physics going on at these energies. But there is one complication, and that's that nuclear resonances can exist. And if they do exist, they can dominate the reaction rate in stellar environments. This plot here is taken from a proposal for a measurement we had for nitrogen-15 alpha gamma, and it shows the several resonances which absolutely dominate the reaction rate. The plot here shows the reaction rate of each resonance compared to the total reaction rate at a certain stellar temperature. And we can see between 10 to the 8 and 10 to the 9 Kelvin, these resonances dominate. And therefore, if we did this extrapolation from higher energies to low energies, it just wouldn't be valid. And this means that we need laboratory measurements either in the energy range of astrophysical interest, or we need some laboratory measurements to tell us something about these resonances. So we want to know the cross-section in our energy range of interest. We can do this either by directly measuring the nuclear cross-section at low energies, which can be difficult if our cross-section is very low, or we can perform an indirect measurement of key nuclear properties. These properties can be things like the spin parity of certain resonance states, and this can tell us about the strength of those resonances and therefore their contribution to the overall reaction rate. Typically, measurements have been performed using a light ion beam, either a proton beam or a helium beam on a heavy target. As Jakob mentioned, I'm involved in the Lunar collaboration as well, which performs nuclear reaction measurements deep underground. And typically we use proton beams on heavy targets, and we either detect the gamma rays using germanium detectors or charged particles using silicon detectors. And this is a technique that works really well. However, what happens if we want to probe radioactive nuclei? A lot of stellar sites that I've mentioned before, such as supernova, nova reactions, a lot of the reactions of interest involve radioactive nuclei. So what do we do in this scenario? Well, we can have a radioactive ion beam, or we can have a radioactive target for our studies. Now, some of you in the audience may already know that having a radioactive target does come with one major drawback, and that's that it will decay over time, and we'll have a disappearing target on our hands for our measurements. And this is definitely not a viable strategy, especially for very short-lived isotopes, which means we've got to focus more on having radioactive ion beams instead. And that brings us to the GSI facility. GSI is a facility that can produce radioactive ions by fragmentation. And then we can then take those radioactive ions, store them in a storage ring, and perform nuclear reaction studies using them. There are several radioactive isotope facilities in the world. These are often fragmentation or isol facilities, but GSI is unique in the fact that we can produce radioactive ions by fragmentation, and then we have the option to store them in two storage rings which are connected. And this comes with some great benefits, which I'll mention later on in my talk. This image here shows the GSI complex. We can see we start with an ion source, we have a linear accelerator, and then what we do is we inject our primary beam into the ring accelerator, which is called the Cis-18. In the ring accelerator, we get up to very high energies, several hundred MeV per nucleon. And once at high energies, we can put this beam to a production target. Now, if we move to look at the image in the bottom left, we can see the path of radioactive ions from their production onwards all the way to our storage rings. So we produce our beam. The production targets are normally beryllium targets, and this produces a cocktail of various different isotopes. We move these through a fragment separator, which is the FRS here. And the FRS separates our isotopes out so that we only get the isotopes we're interested in performing our measurements with. And then we can inject them into the ESR, which is a storage ring shown here. Now, we can either perform our reaction measurement in the ESR, or we can accumulate beam in that storage ring and then inject it into the CRYRING if we want to go to lower energies. And this is where the having two storage rings connected really opens up new possibilities for us, because we can accumulate beam in one storage ring while one measurement is going on in, say, the CRYRING. And this allows us to increase our beam intensity, which for radioactive ion beams is one of the major drawbacks, that intensities are a lot less than stable beams. So once we've got our radioactive ions, what do we do with them? Well, we inject them into our storage ring. This image here shows the ESR, and we can circulate our ions in the ring anywhere from 100,000 to 1,000,000 revolutions per second. So really high revolution rates. And another benefit of storage rings is that only ions with a very specific A over Q ratio will circulate. So if we have some impurities in our ion beam, which remain from the fragment separator, they won't live for very long in the storage ring, because even very similar isotopes are separated when they circulate around the ring. Now, when we inject into the storage ring, we can inject from with energies which are very high. So from 500 MeV per nucleon, we can inject into the ESR. But we want to perform our measurements at gamma window energies. So we need to decelerate these ions to stellar energies. This causes a decrease in the intensity, so we lose some particles when we do this, and it also can increase the momentum spread of the beam. So what we then do is we cool the beam. We could do this via stochastic cooling, but one of the main tools of storage rings is the electron cooler. This electron cooler is basically a section of the ring where we have an electron beam running parallel to the ion beam. The ions in the as they circulate through this section undergo collisions with the electrons and transfer momentum to the electron beam. Now, because the electron beam is constantly renewed, it has a very precise momentum spread, so that the ion momentum spread slowly becomes that of the electrons, and we can get momentum spreads of the order of dp over p of 10 to the minus 5. This also lets us set a very precise ion energy, which is important if we want to study nuclear resonances or very low energy reactions where the cross-section can change quite rapidly. So once we've got a beam and it's cooled, we can turn on our internal target. And our targets in storage rings are ultra-thin windowless gas jet targets. Typical densities are between 10 to the 12 and 10 to the 14 atoms per centimeter squared. This is very low compared to other experiments, but due to the high revolution rate of our ions in the ring, we can get quite good luminosities regardless. Now, we do still lose some energy of our ions through the target, even though it's so thin. In the ESR, energy losses can be several electron volts per revolution, which is a very small amount. But if you're revolving your ions at 1,000,000 times a second, that can add up very quickly. So the electron cooler also works to maintain the ion energy each revolution around the ring. So we're probing the same energy each time. Now, I've got to talk about one of the main limitations for storage ring experiments, and that is the beam lifetime. Now, in nuclear physics, when we hit lifetime, we normally think about radioactive decay. And that definitely plays a role in this. But when we talk about storage rings, lifetime usually refers to beam losses in the ring through interactions with residual gas or with gas molecules in our target. And the lifetime is inversely proportional to 1, the cross-section of our interaction, and also to the gas density. And interactions that are possible are things like electron capture, electron stripping, and also elastic scattering. Now, the reason this is a main limiting factor for some measurements is because if I show you the cross-section for electron capture, for example, this is a semi-empirical formula, but we can see there's a very high dependence on 1, the charge of our ion beam, and 2, the Z of our gas, and also a very high dependence, e to the 4.8, which is our center of mass energy. So if we want to have a reaction happening at gamma window energies, this is very low energy, which means our beam lifetime is much reduced compared to higher energies. And in the same vein, if we want to have a gas target which is hydrogen, this works great because 1 to the 4.9 is still 1. But if we have helium, then our Z is 2. If we want, say, nitrogen, this is 7. It can get much more difficult with different gas species in our target. The plot on our right here highlights the difficulty in terms of a ring vacuum and why we have to have very good vacuum conditions in our rings. So this shows proton beams and also an oxygen beam. So you can see the dependence on our beam charge and also on energy for the same beam. And you can see at 10 to the minus 10 millibar, we have very low storage lifetimes for both proton beams and oxygen beams. Whereas if we go to 1 order of magnitude lower to 10 to the minus 11 millibar, our lifetimes are much easier for us to live with. So now I've talked about the method, I'd like to talk about some of the first measurements that were conducted at the ESR. Now, nuclear reaction measurements, primarily proton capture reactions, have been pioneered at the ESR in recent years. The first measurement of this kind was in 2015, and since then, we've had a few more measurements ongoing. The image on the right here shows a zoom-in view on the ESR for one of our measurements and what the experimental setup looked like for this measurement. So this was for the xenon 124 P gamma reaction. And you can see the xenon beam goes from left to right here and interacts with a hydrogen target. Now, if our beam doesn't react with the target, it just continues to circulate around the ring. But if we get a reaction occurring, we produce heavy nucleus cesium-125. And as this travels through the dipole, it's separated from the xenon beam due to the different A over Q ratio, and is actually bent inwards towards the inside of the ring. And what this experiment did was they placed a silicon detector at that point so that they can measure the cesium coming out of this reaction. Now, the figure on the bottom right here shows the counts in each pixel of this detector. Now, at 0x position, you can see like quite a slight rise, which is due to elastic scattering of xenon onto the detector. You still get some elastic scattering background. But right in the center of the detector, you can see the cesium, which was from the reaction they were trying to measure. What you can also see is some X-ray detectors, which are positioned close to the gas target. And these are actually to measure the radiative electron capture, which come from the interaction of our beam with our gas target. And this is for normalization purposes. Normalization is one of the key aspects of storage ring measurements. This is as our beam intensity decreases over time, as I mentioned, with interactions with the gas target and also with residual gas in the ring. And also, as we're firing our gas jet through our interaction zone, the density of our target can fluctuate slightly. So we need robust normalization techniques. So on the ESR, they use radiative electron capture for this purpose. So now, what does the result look like? So we take our normalization, which is our bottom left result, which is our X-ray spectrum, and they use the KREC peak here to do their normalization. And we take our reaction counts, and together this gives us our reaction cross-section. So this measurement was very successful, and measurements on the ESR were actually approaching gamma window energies for 3.5 gigakelvin stellar temperatures. So we can see that we can now get down to these energies of interest for astrophysical scenarios. And I know this measurement was published in 2019, and I think they've had a few follow-up measurements, and also they've had tellurium-118, and they've measured the P-gamma reaction for that recently as well. But as you may have seen, these are still quite high energies. So the gamma window we're talking about there was at 3.5 gigakelvin. What happens if we want to probe stellar scenarios that are at lower temperatures? So for novae explosions or even big bad nuclear synthesis, well, we need to go to much lower energies, and that requires us to go to the CRYRING storage ring. So this is the next ring in the chain. It was recently installed at GSI and finished installation in 2019. And we installed the CARME reaction chamber in 2021. Now, one of the major benefits of CRYRING is that it can take radioactive beam from the ESR, or we can also inject stable ions from a local ion source and circulate those ions at energies down to around 100 keV per U. And this means that we're right within gamma window energies for a wide range of different stellar scenarios. One drawback is this does require another order of magnitude better ring pressures. So we need 10 to the minus 11 / 10 to the minus 12 millibar vacuum pressures. So extreme high vacuum levels. So if we have a look at the section of the ring that CARME is installed, this is what it looks like. On the left, we have our gas jet target, and on the right, we have the CARME detection chamber. So at the top of the gas jet target, we have these inlet chambers. Now there's several inlet chambers which are differentially pumped. This is because we need to get to the extreme high vacuum levels. We have a cryogenic cold head, which produces our cryogenic gas jet beam, which moves through these differential pumping stages and then into our interaction chamber. Now the interaction chamber is quite nicely visible here because it's got a lovely skull and crossbones on it. And that's because we've fitted a beryllium window to the flange here, so we can put an X-ray detector if we want to in the future. Our reactions happen here, and then our reaction products move towards the CARME chamber, where we have some silicon detectors installed. There's not much to see on the outside of the CARME chamber here. You can see a couple of ion pumps, and you can also see some of our electronics installed on the outside. So what does it look like inside then? So this is a CAD model render of the inside of the CARME chamber. In green, you can see the components of the gas jet. At the top, you can see the differentially pumped sections. And at the bottom, you can see the target dump section. Our ions go from left to right. And in blue on the CARME chamber, we have these squares, which are our silicon detectors. So we have two lots that we can install in the chamber. We have these four, which are closer to the interaction chamber. They're in something called the wall, but we actually don't have those populated at the moment. What we do have populated are the two silicon detectors that you can see furthest away from the interaction chamber, and these are about 1 meter away from the interaction point. So if we have a look at those in real life, this is what they look like. So these four silicon detectors are 10 by 10 centimeters each, so they're really quite big. And each side of our detector, so X and Y, both have 128 strips. So each detector has around 15,000 individual pixels that we can have a look at. Now, they're mounted directly under these XHV vacuum pressures, which brings its own challenges, which I'll talk about in a moment. And everything is under vacuum except for our electronics. So our data acquisition system is mounted onto the top of the chamber. And these gold, orange cables carry our signals from our detector to feed through flanges, which lead to our electronics modules. Now, what you will see is that our detectors are mounted on these two arms, and they're attached to some motors, which actually drive our detectors in and out of the beam axis, which you may think is a needless complication. Why do we do this? It does make our life a lot harder, but our detectors actually need to be made to move due to beam being injected into the ring. And every time there's an injection of beam into the ring, we need to move our detectors. And this can happen quite regularly. So this can happen several times a minute if needed. So why do we do this? Well, when beam's first injected into the ring, it can have quite a large width. several centimeters. And if we didn't move our detectors out of the way, a beam would hit our detectors and instantly destroy them, which is not good for anyone. So what we do is we move them out. And then once the beam has been cooled by the electron cooler, the size of the beam has been reduced to several millimeters, and we can move our detectors in for our measurement. We perform our measurement until a point where the beam intensity is dropped due to these beam interactions, where it's more efficient to dump the beam from the ring and re-inject at a higher energy. So we move our detectors out again, dump the beam, and the whole cycle repeats itself. So what does this look like? This is a video I took during our installation of the detectors to show their movement. So you can see the detectors being moved in, and we can control the position of these detectors quite well. I think the precision is around the 0.1 millimeter range. Now, what you'll see is the hole in the center of the chamber is actually the beam pipe, which the beam goes down. And if we, at the start of where the ejection cycle, when beam is first injected, beam can cover this whole pipe. So we need to move the detectors out of this zone. And you'll see now that when the detectors are fully in, that small gap in the middle is the size, is space for the beam to go through. So the beam is smaller than that size as well. So you can see the difference in beam size when it's been cooled by the electron cooler. It's really quite a lot. So I mentioned all this is under vacuum, and that is one of the main challenges to doing a technique like this. So we want to get to 10 to the minus 11, 10 to the minus 12 millibar. And this requires several things. One of them is vacuum compatible materials. So all of our detectors are custom made, especially for extreme high vacuum conditions. We also have all of our cabling. We can't use regular ribbon cabling because that would just destroy the vacuum instantly. So all of our cables are capped uncoated. And in fact, these were all handmade by myself during my PhD in Edinburgh. And the white you can see here is for strain reliefs, because we'll be regularly moving these cables. So to relieve strain on the cables, all this has to be in Maycore as well, which is a special kind of ceramic. Not only do we need these materials, but we also need high pumping speed. The picture on the bottom left here shows a neg getter, and we have 13 of these installed in the chamber, as well as several ion pumps and a couple of turbo pumps. And in total, we have over 20,000 liters per second pumping speed in our chamber, just to keep up with the small outgassing rate we have for this XHV kind of pressures. Not only that, we have to clean everything before we install it. And even then, we still have to bake out the entire setup. So because we've got our detectors, and they've got a rating of about 150 degrees maximum before things start to break on them, we limit ourselves to 120 degrees for the bake out, which means we've got to bake out for more than 2 weeks, just to make sure we drive out all of the water from our chamber and all of our setup to get to these pressures. This was one of the main challenges, and it's something I spent most of my PhD doing. You can see, if you're interested in how we tackle these challenges, this NIM paper I've linked to here has most of the stuff about how we conquered this vacuum challenge. So that brings us to our commissioning measurements. So we conducted some measurements in 2022 and also 24 using stable beams, and this was to commission both our setup, so the CARME array, but also the gas jet target. So in 2022, we did the measurement of nitrogen-14 DP using a deuteron beam at 3 MeV onto a nitrogen-14 target. This was the first use of the gas jet target at CRYRING, and also the first use of the CARME array. Unfortunately, at this time, we only had one detector installed, so it wasn't a full commissioning experiment. However, in 2024, we had all of our detectors installed, and we were able to perform 2 more measurements, one using a helium target with an oxygen-16 beam, and one using a hydrogen target using a nitrogen-15 beam. And both the measurements we performed this year we're looking at resonance scans, which I'm not going to talk about right now. I'm going to save that till the end of my talk. Since the analysis is still ongoing for these measurements, I'm going to mainly focus on the nitrogen-14 DP measurement. So first, I'm going to talk about the commissioning of the gas jet target. We had to demonstrate that it worked effectively. And one of the main things about storage rings is that when you inject an ion into the ring, it has a certain orbit, and different ion beam species and also different charge states. So if you have nitrogen 1+, its orbit around the ring will initially be quite different to 5+, say. So you have to tune the ion beam onto your target position every time. And then once you know where it's tuned, you can save those settings for later. But finding this target beam overlap is one of the main things you've got to do first when you perform a measurement. Thankfully, with heavy ions, they have a beam lifetime when they're corresponding to residual gases. But if you tune them onto the target, this lifetime is greatly reduced. So you can use that to find where the overlap is. The image on the left here shows the number of particles circulating in the ring at injection and also at dump, so at the end of the cycle. And you can see this massive decrease in the number of particles when we've got beam target overlap. And the plot on the right here basically shows we move the horizontal beam position by small increments, and we waited to see when the beam loss percentage increased. So without the target, we get in beam losses of around 80%, whereas when we're hitting the target, basically 100% of our beam is lost in each cycle. Now for nitrogen-15, we observe this sharp decrease in beam lifetime. For deuteron beams, the lifetime is much greater, so we also had to rely on some elastic scattering and looking at the rate in our detectors to tune the beam onto the target. Now, once we've done that and we've got our reactions, we measure our signals from our detectors, and then we get some output from our DAQ. And this brings us on to the next thing we've got to do, and that's look at ring cycle timing. So output from our DAQ, we get an X and a Y position, as well as an energy and a timestamp. And we use this timestamp to differentiate between the different ring periods. So we have different time periods in our ring cycle. There's injection of the beam. This beam has to be accelerated to the correct energy. There's cooling, and we're also moving our detectors in and out. This is a lot of stuff that we don't want to include in our final analysis. So we put some signals into our DAQ, which tell us when detectors start and stop moving. And this enables us to cut out all these periods we don't want to see, so that we only consider events that happen when cooled beam is in the ring and our detectors are stationary. So this plot here shows the number of events in our detector in black. And then the first signal corresponds to the detectors moving out of the beam axis as beam is dumped from the ring. Our second signal tells us, okay, the detectors have stopped moving, they're out. Then there's a bit of time with no beam in the ring before it's re-injected. And then the third signal goes, I'm going to move the detectors back in. And then the fourth signal tells us the detectors have stopped moving. Now we can start a measurement period again. And what we do is we look for these signals, and anything between signal 1 and signal 4, we just discard, and we don't do any analysis on those. And then we can get a plot like this, which can actually show you the ring cycle as well. So this plot shows you an energy histogram against the time in the ring cycle. The time is in tenths of second here, so it goes up to 700. That corresponds to 70 seconds. And time equals 0 corresponds when the detectors first get that signal to move in. So signal 3 on the previous plot. So after 2 seconds, the detectors are stationary and the measurement period begins. After 60 seconds, measurement period's up and we dump beam from the ring. And then after 70 seconds, we re-inject. So what can you see in this? You can see after 2 seconds, we have this nice bright band at 3 MeV. And that is our elastic scattering of beam onto our detector. This is nice. This is what we expect when we have beam on target. We also see some bands which are slightly less bright at higher energies. The one that this arrow with stable measurement period is pointing to is at 4.2 MeV, and that's actually a nuclear reaction peak. Then the beam dump at 60 seconds, we see these bands disappear as we have no beam in the ring. Some things to note here as well. We have some low energy, I call them noise events, and this is due to detector movement. You can see some spikes in the rate at 0 seconds at around 500 kV, and the same at 60 seconds and the same at 70 seconds. This is from the detector moving, but what was really nice to see is that this doesn't last for very long. It's very short-lived, so it doesn't impact our stable measurement period at all. What you can also see is we get some high energy events when the beam is dumped from the ring, and that is probably just from beam particles that are dumped hitting our detector all at once. But what this plot shows is that we have a very nice way of separating our events, and we have a stable measurement period. Now, I mentioned normalization previously for the ESR, and we also have to do a normalization procedure, but we use elastic scattering. The reason we do this is because our detectors are at very narrow angles, so the elastic scattering rate is very high. In fact, the bottom left plot here shows the count rate across the number of counts for each energy. And you can see at 3 MeV, which is the scattering energy, you see this huge peak, and it's so big you can't even see anything else. And that talks to the domination of elastic scattering in our detectors. And the plot on the right actually quite nicely shows the elastic scattering across the detector. So we have very bright picture here in the bottom right corner where the beam, close to where the beam is, and this decreases across the detector. So for our reaction measurement, we have this equation for the differential cross-section with our number of detector counts, and then we have our parameters for beam intensity, target density, etc. Underneath it in the equation. Now, all of these parameters can change slightly. So what we do is we lump them all into this normalization factor. And if we know the number of elastic scattering counts, we can determine this normalization factor and use this to normalize our cross-section. So what is the uncertainty on this? Well, elastic scattering is very well known. We can say there's essentially no uncertainty on that. But there is an uncertainty on our detector position. Because we're at such narrow angles, if we're out by even a small amount, say 0.1, 0.2 degrees, this can have a very big effect on the elastic scattering rate due to the very high angular dependence of elastic scattering. So we need to know the detector position with very good accuracy. Now, thankfully, with our motors, we can know the position of the detectors within 0.1 millimeters, but that's just, it's not an absolute position. So we also check that with by fitting our data with the elastic scattering cross-section. So the plot on the left here shows something from our nitrogen-15 beam time this year. We see some counts at different center of mass angles, and we fit the elastic cross-section. And if you vary what we assume for the detector position by even a few millimeters, the fit just goes, it looks terrible. So we know we've actually got a very good position. But can we check it by another way? We can. If we perform a reaction in inverse kinematics, we get this closed kinematic loops. So the scattering and actually some reactions in inverse kinematics as well have a very well-defined maximum angle which events can be detected at. And this is shown in this image here for nitrogen-15. And this maximum angle is around 3.8 degrees. And what we can do is we can just isolate in our detector all the elastic scattering counts. And then if we plug them into the XY plot on our detectors, we see a very nice image of this nice circular distribution. And we can simply just line up our detectors so that it all fits very nicely. So we're pretty confident in the position of our detectors using these two different methods. So once we have a normalization factor, then we can look at our nuclear reactions. So I'm going to go back to our commissioning experiment, which is the nitrogen-14 DP. And this plot here shows an energy spectrum for all the counts observed, and this is across all detector angles. This is important because you can see there's we've labeled all of our different reaction peaks. So we observe some d-alpha reactions and some dp reactions. These are labeled in blue, but we also have some labels with red stars, and that's for some detector edge effects or some pile-up from elastic scattering, which when you eventually cut away an angle, these disappear quite quickly. But another thing you may also see is we have very low count rates for some of these reactions. This is partly because we had one detector installed at the time, so we're suffering a factor 4 hit on our detection efficiency there. But also this was the first time we had the target on the CRYRING. We were doing the target commissioning during the experiment. And this meant we had very low target densities. of the order of 10 to the 11 atoms per centimeter squared throughout the whole beam time. And this is very low. For example, on the ESI I mentioned, they can get up to target densities of 10 to the 14. So we're several orders of magnitude lower than where we want to be. So that's why the count rate was significantly lower for this experiment. But if you look to the very left of the plot, you can see this peak, which corresponds to the DP reaction to the fifth excited state at 4.2 MeV. And we saw quite a few counts, and this enabled us to get an angular distribution, even just for a few points. So on top of this, I did a DWBA calculation using Fresco. And then we plotted it against some previous measurements, which were taken from the 1960s, in order to compare our cross-section to previous data. And what we see from the plot is, compensating for the different energy scales, our result looks quite nice compared to previous data. And when I extracted the spectroscopic factor by comparing the DWBA calculation for the cross-section to that of what we got in the experiment, this also was in line with previous experiments. So we were quite happy with the result in the end, and we were able to say, okay, our setup does work. So I'd like to just give a brief overview of our commissioning experiments. So now in 2024, as I sit here, we've got all of our detectors installed and they're all operational. You can see them in the picture here. The gas jet target has been commissioned with all of the targets that we want, so all the beams, target species we want. So we can get hydrogen targets, helium targets, we can get nitrogen targets, etc. However, we would like higher target densities in the future. In the previous beam time, we were getting up close to 10 to the 12 atoms per centimeter squared, but not for consistent periods of time. So this is one area of improvement we have. And also, actually, in the latest beam time, now we've got all 4 detectors, we were able to see some more beam-induced background, and we now understand this a lot better. There's still some improvements to be made here. And on the previous image, some of you may have spotted this stripe that seems to go across the center of our detectors. This is actually a beam halo effect, which we only noticed when we had all 4 detectors installed. And we're currently undergoing some improvements in that. We're going to put some scrapers in so that we can reduce this background as well. The 2024 measurements are currently under analysis, but we've got many more measurements to come. And that's what I'd like to use my remaining time to briefly talk about. So I briefly mentioned Big Bang nuclear synthesis at the start of my talk. It's where the light elements up to lithium are produced. And one of the really cool things about Big Bang nuclear synthesis is we can use our predicted abundances from BBN models and compare them to observations of very ancient gas clouds from the early universe. We can compare those, and this allows us to probe our parameters in our Big Bang nuclear synthesis models. One of these parameters is the baryon density, and space satellites such as Planck can give us an independent reading of those as well. So that's an extra data point for probing BBN models. Now, deuterium is of interest for this. It's a really good probe because it's got high dependence on the baryon density. And also observations have uncertainties of the 1% level. Our nuclear physics uncertainties are really good as well. But if we can improve them, then we can start to probe these Big Bang models a lot better. Now, the main physics uncertainty to be reduced is the D plus D reactions, which are highlighted in red in this plot here. And we believe that with a measurement of CRYRING, we can go down to around 100 keV per nucleon beam energy. And this would correspond to the very center of the gamma window for Big Bang nuclear synthesis. So this is an experiment we're going to perform in 2025, and we're very excited to do this next year. Also, we have some plans to study some resonant elastic scattering. Now, earlier in the talk, I mentioned that some of the measurements we did this year were looking at resonances in nuclear reactions. We used oxygen-16, for example. And the reason we want to do that is because we would like to do some resonant elastic scattering experiments to measure the excitation function at very backward CM angles to obtain some nuclear properties of interest. So what we'd want to do is use an oxygen-15 beam, have this on a helium target, and At higher energies, we'd see our Rutherford scattering, which we would use for our normalization. And then at lower energies, we would see this elastic scattering, which we can probe this excitation function with. And on the left here, you can see the excitation function with different nuclear parameter assumptions, so with different spin parities of certain states, and also with these states having different widths. And you can see this can produce quite a drastic effect on the excitation function. And it'd be our plan to measure this, but we need really high excitation energy resolution. And thanks to the electron cooler, giving us a very precise beam energy and an ultra thin target with very low energy loss, we think we can do this for this measurement. Now, some of you in the audience may have seen on that plot, it was we're trying to probe the neon 19 excitation function. And this is because for the fluorine 18p alpha reaction, the reaction rate at nova energies is dominated by resonances in the neon 19 compound nucleus. And these resonances can interfere with each other, and this can cause a lot of uncertainty in the cross-section at lower energies where we're interested in for nova explosions. Direct measurements of this reaction are very difficult to perform. So what we try to do is this elastic scattering measurement to try and tell us something about neon 19, which can help reduce our uncertainties on the reaction rate. And then lastly, I'd just like to mention a really exciting plan for bare ion reaction measurements. This would affect electron screening. Screening is a phenomenon which affects all charged particle nuclear reactions at very low energies, and it leads to an unknown uncertainty which affects all quiescent scenarios, so those happening in our sun, for example. And what is it? Basically, in the laboratory, all of our targets have electrons which shield the nuclear potential, and therefore our laboratory measurements have a higher cross-section compared to those in with the bare reaction cross-section, which we expect in stellar scenarios. The plot on the left shows an example of this. So there's a measurement of helium-3 dp in inverse and normal kinematics, and there's some slight diversion in the S factor for the reaction with different beams and target setups. And both of these are higher than the predicted bare S factor, which highlights the problem with this measurement. So what would we do about that with CARME CRYRING? Well, luckily for us, there is an upcoming installation at the end of 2025 called PHYSIC, which would install a transverse ion beam, which would enable us to have an interaction between the revolving ions going around the ring and this ion beam. So we could have a proton beam, for example, which interacts with our revolving ions in CRYRING. And this would give us the unique possibility to, for the first time, perform a bare nuclear reaction measurement directly at these low energy stellar energies. Now, we can also turn off our ion beam and turn the gas target back on. This would allow us a direct comparison of the screened nuclear reaction and the non-screened reaction. So this is a very exciting project which we hope to perform in the next few years. So I think I'll leave it there. Thank you very much for your attention. And I'd like to thank all our collaborators on the CARME project. These are the people that have helped us out at GSI and also from Frankfurt University. There are several more people that, too many people to fit on one page, that have helped us out with shifts as well. So thank you to everyone.